Hi everyone, we are finally there. Thank you very much for the patience and welcome to the session with Dr. Sabine Kastner. We have an interesting situation where one of our moderators is now going to change the slide, and we hope to have like a nice and decent narrative with what Sabine is saying and what Nico is interpreting and changing the slides. Let's see how this goes, and I'm looking forward to this. So before I introduced her, there's a few technicalities I will talk about. You can ask questions using the Ask a Question feature down there, and then you can also tell whether you want to be invited on the screen or not for it. And with this, I will introduce her then. So Sabine did her PhD here in Göttingen at the Max Planck Institute for Biophysical Chemistry, and then she conducted her postdoctoral research at the National Institute for Mental Health in the US. She is currently a professor at the Princeton Neuroscience Institute and will today talk about the neural dynamics of primate attention network. So with this, I hand over to Nico and Sabine.
Thank you very much. So we'll see how this will go. It will be an interesting experiment. Thanks for your patience to wait for the technicalities here to be resolved that were not resolved in the end. But we'll try our best, and thanks to Nico. So he has to really listen very closely. So I'm really happy to share with you some of the electrophysiology work that we have done on the primate attention network during the last few years. And I want to start with one of my favorite artists. This is a painting. Nico, you need a forward. Thank you. This is a painting by René Magritte. And I will not go into the philosophical dimension and the implications for visual perception of this painting. I just want to say that this painting is just as fresh in its deep meaning in the era of Corona than it was almost 100 years ago when René Magritte painted it and called it the human condition. So now let me start to go into what the topic of my talk will be. So when we are faced with complex scenes like this painting, what we typically do in order to select the information that is relevant for our ongoing behavior is to recruit a spatial selection mechanism. This mechanism is often called a window of attention or spotlight of attention. And what the characteristic of this spotlight is that it is operating only over a confined small part of the visual space. And from that space, this spotlight takes in information in a privileged or preferential way. Now, what we can do with the spotlight is we can move it around, so to different parts of the scene until we have gathered the information that we are interested in. And we can do that in several ways. One way is to do it by moving our eyes. We can do that at about every 250 milliseconds or so. That would be in an overt way, or we can do it in a covert way, which means that we can move it even quicker, so every 50 or 60 milliseconds. Now, I want to tell you today a little bit about the neurobasis of the spatial selection mechanism, and we want to take as our starting point what happens in the human brain during a spatial selection of the type that I just illustrated. What you're looking at here is a right hemisphere of a human brain. This is a reconstructed cortical sheet. It is inflated. And we see here in an animation functional magnetic resonance imaging signals floating through this brain. So you see a buildup of activity over the occipital pole first. And then later on, there's also a buildup of activity over the intraparietal sulcus that is very prominently viewed here in this kind of bird eye view that we have on this brain. And there are also activations in frontal cortex that you cannot appreciate as easily in this view. Now, the point I want to make is that during a selection that typically takes about 200 or 300 milliseconds, there are hundreds of nodes at work that need to be coordinated to route the information that we're processing through our brains. And we are interested in understanding what's going on in each of these nodes and how these nodes are interacting during a spatial selection. So I'll tell you a little bit about that today. So the way we approach that is that we are studying two brains, the human brain and the macaque monkey brain, and we are using behavior that we establish in both of these species to basically glue them together. And our behavior is always informed by human cognitive psychology. So we typically start with a task that is very well established for humans, and then we train our macaque monkeys in that task, and we try to establish common behavior. And then we try to relate those behavioral signatures to neurosignals from neuroimaging and electrophysiology. And we do the electrophysiology in both species intracranially. So in humans with epilepsy patients, I'll tell you a little bit about that in a little while, together with Joseph Pavizzi and Bob Knight. Now, let's go to the next slide. I want to start with the behavior, the specific behavior that we studied in this series of experiments. So in this task, it's called an Egli driver task. So it's, again, a very well-established, very classical spatial attention task. So it starts with a fixation point. Our subjects are simply keeping fixation. There's never an eye movement during this task, so all what happens here happens covertly. Then there will be the presentation of two bar-shaped stimuli. They could be oriented vertically or horizontally, so this will change from trial to trial. Then we show a cue and one of the four corners, so here in the upper right, which is then followed by a variable Q target interval. And then we show a target in the cued location with a high probability, about 80%, and that target is at threshold. So it's very faint. It's fainter than what you see in this demo here. Now, what we were particularly interested in this study was to look at the Q target interval. That is the one with a frame here. So this is just a summary of the sequence of events that I just described. And we were interested to see what happens when attention is allocated at the cued location. What happens over time? Is this like a constant process, or is there some temporal dynamic in that? And what we found was quite amazing. So here is first the result from humans. So this was not known before we started, this property of this spatial attention task. So what you see here is the hit rate as a function of the Q target interval. So let's say we have a Q target interval of about 400 milliseconds. At that point, you are in a peak. So you are about 5% better at, let's say, 120 milliseconds later when you are in a trough. And then you go back to a peak and to a trough and so on. So there's a behavioral oscillation going on here. That means attention allocated at that location is not constant over time, but it seems to wax and wane and goes through periods when we can extract more information from the environment and other periods where we can extract less information. And that behavioral oscillation goes at about 4 to 6 hertz. Now, since we wanted to look at this task in non-human primates, I lost a little bit faith at that point because for some reason I didn't think that non-human primates would show these rhythmic properties, but to our surprise, they do. So here you see the same behavioral signature in two monkeys, and this made these behavioral oscillations really much more interesting because now we are looking at a property of attention that has been preserved for at least 20 million years in primate evolution. So let me summarize briefly where we are right now. So I've shown you that there are behavioral oscillations that go at 4 to 8 or 6 hertz during visual spatial attention. They set up alternate states of better or worse performance, and these rhythmic properties of attention are preserved throughout primate evolution. So let's go into the So basically what this means is that when attention is allocated, just click on it again, Nico. What this spotlight is doing, it's basically blinking. So it's waxing and waning and going through these periods of better or worse performance. Now, let's go to the next slide. So I want to tell you a little bit about the neurobases. Keep in mind that we are not subjectively aware of these behavioral oscillations or rhythms. They do not render us blind in any way, but again, it's something that is automatic, that is not really in our control. So I will tell you first about a few results from our human electrocorticography studies. So in electrocorticography, patients, these are typically epilepsy patients, are being implanted with electrode grids. So here are two scenarios from surgical from surgeries, and the strategy behind these implantations is to prepare the patients for the removal of the epileptic tissue and put them through a number of diagnostic procedures. And this takes about 1 week. They are on an intensive care unit during that period of time. And the coverage of these implanted electrodes can be very variable. You see that here in 4 examples. So what we typically do is we take a cohort of patients. So these coverages are dictated by clinical criteria, by the clinical scenario, not by any scientific purpose, obviously. And when we put a cohort of patients, like 8 patients or 10 patients together, then we get a really wonderful and broad coverage. As you can see here in a lateral, a medial, and a posterior view of this brain here in normalized space. Then you can combine these electrode coverages in these normalized spaces with atlases that are readily available now, and you get a good idea where some of these electrodes are located. So the signal that I will discuss most here, or let me talk a little bit about the ECOG signal in general. So this is a field potential that you see down there in the lower left. And this field potential is fueled by probably thousands of neurons. No one knows really how many there are. And what we can do with this complex signal is we can filter it into the frequency domain, and that's what you see in the upper right. And the signal that is the most prominent and has the strongest amplitude is a broadband signal above 70 hertz. This is the high frequency broadband response, and I will focus on that particular frequency band in the following part. Now, let's look at the high frequency broadband response during just a single trial from one electrode in posterior parietal cortex in one of our patients. So you see again the sequence of events and the task, and at time point 0, that's the onset of the cue. So you see a cue-evoked response. Then there's a cue target interval, which is quite long in this particular trial. You see right away that there are fluctuations during that cue target interval. Then the target appears, that's the black dotted line, and the green line denotes the manual response, the key press. So right away, you see that there are these fluctuations that go on during the cue target interval, even though there is no change in the sensory environment. It's just the allocation of attention in space. So I show you a couple of more trials just to make the point that this is not happening just in our best trial, but it's a regular finding. Now, the interesting thing is that these fluctuations even happen in the third trial, the lowest one, when the subject actually is missing the target. So that's just an interesting feature of these 3 trials here. So the next question that we asked was, what is the frequency of these fluctuations that we are seeing here? No, you have to go back, Nico. I'm not there yet. And the analysis that we did was a peak-triggered average that you see to the left. So what we do there is basically we take one of these peaks in the fluctuations, and we take a window 500 milliseconds before and after, and then we move over and so on and so forth. And we do that, you know, for all of our trials and for each electrode and so on and so forth. And as you can see, there's a 4 Hertz neuronal oscillation going on here. It's fitted here with a sinusoid in the raw potential. And so what we're looking at here is now a behavioral oscillation that's at 4 Hertz and a neuronal oscillation at 4 Hertz. But that does not mean that these oscillations have anything to do with each other. So it could just be a coincidence. So we wanted to see whether we can link the behavior and the neuronal responses more closely. And what we did, so go to the next slide now, but don't show this yet. Just take that away, go back, thank you. So I want to go back to these 3 trials to give you an intuitive understanding of what we do here. So we try to link the appearance of the target to the phase of that 4 Hertz or theta fluctuation that's underlying here and seems to control these fluctuations in broadband response. So if you go to the first trial, when the target appears, that's the dotted line, exactly, it is close to the peak of that theta oscillation. This is also true for the second example, but in the third example, when the patient actually is missing the target, you see that this coincides with a trough of that underlying oscillation. So we basically systematically linked the target appearance to the phase of that theta oscillation. And what we saw, and now you can go to the next one, is a very clear dependence of the ability to detect the target as a function of theta phase. So here you see the phase of theta and in relation to the hit rate, and you see that there's a very clear peak and trough. So there's a phase detection relationship between the two. Theta phase, so the neuronal oscillation, is predictive of behavioral outcome. And that was a really nice outcome of this study, that we were able to link this neuronal oscillation directly to behavior. So these phase detection relationships, please go to the next slide. They are not just found in parietal cortex, but they can also be found in frontal cortex. This is one example here from one patient. So these red spots that you see are regions where you have strong phase detection relationships. And the bluish colors or the cold colors are some where you would not see anything. So let me summarize briefly what I've shown you here in our human ECOG data. So I've shown you that high frequency broadband power is modulated by theta oscillations across a frontoparietal network, and target detectability depends on theta phase. Now let's go now to the monkey data. And I will show you, and this is so at this point you may ask yourself, why would you even need monkey electrophysiology? And I will show you actually how much further you can push these findings if you can go and have availability and access to single cell physiology. The other thing that you can do is you can study regions in the brain that are non-charted in the human brain, and one of those regions is the thalamus, and many of you probably know that we study the thalamus, but I will not have time to tell you about those studies today, but keep that in mind as well. So the results that I would like to show you are from two regions in frontal and parietal cortex. So we had seen in the human data that frontal parietal cortex sets up these phase detection relationships. So we were interested to see what's going on in the monkey frontal parietal cortex, excuse me. And we recorded simultaneously in our EGLI driver task from the frontal eye field and the lateral interparietal area in posterior parietal cortex. And before I move on, I would like to kind of reconceptualize the frontoparietal network a little bit for you. Very often it is conceptualized as an attentional control network, and undoubtedly there's some truth to that, but I want to kind of portray it a little bit different here. If you go to the next slide, I want to take the single neuron responses that I will get back to here as my case. So one way to think about the frontoparietal network is actually as a network where two different networks are coming together and need to be integrated. And one is the visual processing that comes from downstream areas, V1, V4, and streams into parietal cortex and frontal cortex. And the other one is actually the oculomotor system. So these are signals from the superior colliculus, from other motor structures and frontal cortex that are also reflected in these neural response properties that you typically find in these two regions. So what you see are there are neurons that respond only to visual stimuli. The checkerboard is from here on our visual processing icon. So you see here neurons that respond to visual stimuli, but not during saccadic eye movements. So the eye movement icon is the oculomotor icon, if you like. Then you see the opposite. You see movement neurons there. So neurons that would not respond to visual stimuli and only respond during saccadic eye movements. And then you see a mixture of the two visual movement neurons. So if you think about these two different network parts, visual processing and oculomotor, they are actually in potential functional conflict. When you are trying to take in visual information, you should not move your eyes. And if you move your eyes, you cannot take in visual information. It's as simple as that. So these two parts of the network need to be coordinated in some way to avoid that functional conflict. And what I will argue for today is that this theta rhythm is the mechanism by which this functional conflict gets coordinated and resolved. And so I will show you some data now to convince you that my thesis has some empirical basis to it. Now, the first thing that we did here in our investigation was to look for these phase detection relationships that we had seen in the human brain in these two regions in the monkey brain. So we are looking for something that looks like the profile of hit rate versus theta phase that you see down there to the left, rather than to a flat profile. So we are looking for, a clear peak and trough, so a theta phase that is predictive of behavior. And as you will see in the next slide, we see these phase detection relationships very strongly at these typical frequencies where our behavioral oscillations can be found in the frontal eye field and also in the lateral interparietal area. Now, go to the next slide. So here, theta phase is basically setting up, if you like, a good phase during which the behavioral performance is better, and a poor phase during which the performance is a little bit worse. And this good and poor phase, this is kind of how I will, in going forward, talk about these two different phases. Now, in the monkey data, we were able to also look at higher frequencies because we are having now a much richer data set, many more trials than in our human ECOG studies. And that allows us to see whether higher frequencies are also setting up phase detection relationships, so they are also predictive of behavior, and if so, whether they would be related to the good or the poor theta phase. And here I show you the results for the frontal eye field. So what we see there is that beta signals between 20 and 30 hertz are actually predictive of behavior, but only in the good theta phase. They can only be found in the good theta phase, not in the poor theta phase. There's nothing really going on here. Now, in the lateral interparietal area, we see a little bit of a different pattern. That's the next slide, yes. Here we see that during the good theta phase, we have a prominent gamma activity that is, again, predictive of behavior, sets up phase detection relationships, but only during the good theta phase. During the poor theta phase, we see actually a very prominent alpha signal that is predictive of behavior. And I will not discuss that further, but that is a signal that is related to thalamocortical interactions, and I'll be happy to take questions on that if we have time during the QA. But I will not talk much about it further. So with all that now, with all these interesting relationships of oscillatory activity in these different brain regions that are predictive of behavior, I want to kind of start building a new attention model. So I want to summarize the results thus far schematically. So what we have thus far is that there is a theta rhythm in both regions, frontal eye fields and LIP, and that theta rhythm actually is synchronized. I didn't show you the data, but you can take my word for it. Across these regions, and the phase of that theta is predictive of behavior. It sets up a good or a poor phase with relation to behavior. Now, what we see prominently in the frontal eye fields is beta activity during the good phase that is predictive of behavior, and it is actually nested with the theta oscillation. That means that the theta oscillation is, no, we're not there, sorry. The theta oscillation is controlling the strength of the beta activity. So it's really strong during the good phase, but then it is much weaker during the poor phase. And the same is true for the gamma activity in the lateral interparietal area, which is also, again, it's nested to this theta oscillation. Now, let's go to the next slide. So we asked ourselves at that point, where we saw all these major oscillation frequencies that you can see in MEG and in EEG studies, and of course also in non-human primate electrophysiology physiology studies, what does this all mean? And we got more clarity about a possible interpretation when we actually went back to the single units and to the properties of the single units and tried to relate these different neuron types that I introduced earlier to some of these oscillation activity that we have seen thus far. So we asked the question whether the spiking activity of neurons in FEF and LIP, of visual neurons and oculomotor neurons, is specifically related or may be specifically related to some of these oscillation frequencies. And so what we looked at here is the spike field coherence measure. So we are looking at spiking activity in the lateral interparietal area in relation to local field potential activity in the frontal eye fields. And what we saw was that the visual neurons are exclusively correlated, clustered with gamma activity locally in LIP as well as in FEF. So the idea here is that these visual neurons are routing that information to FEF using that gamma frequency band. Now, gamma activity in the visual system has been very prominently associated with visual processing. So that was corroborating a lot of the existing literature. But keep in mind here that only visual processing neurons establish this relationship. Now, on the other hand, the oculomotor neurons, they are tied and linked to beta activity. And here the spiking activity, so the oculomotor neurons spiking in the frontal eye fields, are actually linked to that beta activity locally in the frontal eye field, but also in the local field potential that you can measure in LIP. So these neurons seem to send signals to LIP. And as probably many of you know, beta activity has been frequently associated to present some kind of top-down feedback signals. And that's certainly true here too. But we think this is a much more specific signal that, again, is linked to these oculomotor neurons. So let's see what's going on here. So our interpretation of these beta signals is actually the following. Beta in the motor system has been typically associated with a suppression of movements. So what we think is going on here is during that good theta phase, sampling from the environment, so the take-in of information from the environment, is promoted by ramping up visual processing, which is the signature of here is the coupling of visual neurons to gamma activity. And at the same time, the suppression of the oculomotor system by the strong beta activity. Now, that is one attentional state that you get during that good phase that promotes the sampling of information from the environment. During the poor phase, on the other hand, go to the next slide, we get a release of suppression from the motor system, and we get a slightly ramped down of these visual processing resources. And together, this might enable the shifting of attention to a new location if we get interested in something new. We may just decide to stay with our allocated attention where we are and then go back to our sampling state. But we basically have an opportunity every 250 milliseconds to shift attention more easily, if you like. So basically, the way attention works, this cognitive resource is setting up alternating states during which either sampling is promoted or shifting is promoted. And we think the system is set up in this way to basically give or provide the most cognitive flexibility. So rather than locking into one state and getting out of that state and getting into a new state, here we go to these alternations just seamlessly, and that gives us the flexibility we have to just, allocate attention to new locations in a really, flexible and quick way. Now let's go to the summaries. Next slide, please. So I've shown you that attention function unfolds. No, sorry, one back. Attention function unfolds over time and has rhythmic properties. We saw that theta oscillations organize sensory and oculomotor networks into these two alternating states for sampling sensory information versus shifting attention. We think that is the key to understanding cognitive flexibility. And also keep in mind that this is the mechanism by which this functional conflict that occurs in the frontoparietal attention network is resolved. Now, to give you a little bit more broader picture ideas here, one really important take-home message is that cognition unfolds over time. Very often we throw out time as a dimension in the way we design tasks, but as you have seen here, time is a really key parameter to understand cognition. By looking at time, we end up with a new attention model that assumes these alternating states. And we actually think that these attentional rhythms may be a hallmark of a healthy cognitive function. And so we think that in conditions like ADHD, these rhythms actually may not exist in the same way as we measured it here in healthy attention function. Obviously, that is something we need to determine, but that will be an interesting, future venue for us. And now I want to close with two announcements. If you are interested in questions like this and you want to do some experiments with me, we have postdoc positions available. So if you graduate soon, keep us in mind and send me an email. We'd be very interested, to talk to you. And one other announcement, that is for all the young scientists, and I think I'm talking to a lot of young scientists today, even though it's a little bit like a Geisterspiel in the Fußball-Bundesliga, what I do right here, because I can't really see you. But I know that there's an audience out there. So many of you probably know that I'm involved with public outreach and science education for many years. And one vehicle that we have created with a large number of colleagues is a grassroots movement of scientists, is this kids journal. It's open access, and we need the involvement of young scientists. So this is a really wonderful way to give back to society and educate the next generation of scientists. And if you want to become involved, again, just shoot me an email. I'll be happy to talk to you about it. And with that, I thank you for your patience and long attention span.
Good. I will try to. Great. Thank you very much for the great talk.
Oh, thanks to
last
Nico.
time I met
He
Sabine,
did a great job. So
I wish I had some electrodes implanted right now, so we can evaluate my very interesting attention task here. Also with
last
time
time
lag.
I met Sabine, we ended up we had. There is a time lag. Great. Her work on the stuff she writes is very inspiring, and the website is absolutely great. I highly recommend looking at it. I was so inspired by it. We ended up just talking about that website instead of talking about science the last time we met. Okay, we have also very interesting questions, and I will invite Jaime on the screen for this. And Nico, you're kicked out now. We will wait for him to come on the screen, and he wants to ask it himself.
Okay.
Should be connecting soon. Yes, he has accepted and he's coming soon. Interesting. Okay, so his camera blocks him, so I will end up reading this for him. He says, there is evidence that our perception is not a continuous, but rather a discrete process. How can we distinguish if these behavioral oscillations come from attention enhancements or are due to sampling of visual information? Are the neural oscillations in the theta frequencies acting as a clocking mechanism that binds multiple circuits? Or are there behavioral states when these oscillations are not present and hence there are behavioral impairments?
Yeah, I think that there are lots of questions in there. It's not only one question. So I think an important message is that, yes, there are networks that get coordinated, right? That's the idea here. So you have an oculomotor network that has a lot of other parts to it that we have not, measured activity from. So you have the colliculus, you have structures like the basal ganglia, there are premotor areas that will play a role here. So you have a whole motor network that's associated with that. And we think that the theta frequency or that theta oscillation in the first place is coordinating the sensory processing with that motor output. So in a very broad way, you can think about it as we are going from a more sensory state where we are sampling information from the environment to a more motor state, and then we go back to a more sensory state. And that's kind of like a default state that is just, again, it's nothing that we perceive, right? But that is basically probably the most efficient our brain has come up with. Is this something that is just modulated by attention and is basically happening all the time? We don't know. But it is my assumption that we basically always have this kind of fluctuating, broad fluctuation between sensory processing and motor processing. And what attention is doing is basically it's kind of sharpening, right? It's probably aligning these things in time more tightly. But I don't think it's basically these rhythms are set up by attention. That is at least my working hypothesis. We have not measured that, or it's very difficult to get at that, but I think these network rhythms always exist, and they get modulated, they get sharpened by attention, or by the allocation of attention. That would be my assumption. Anything else? There was a very
yes.
Is there something I've missed in that question? I mean, it was a very complex question.
I think you answered to most of them. So Jaime, if this isn't clarified, you can write in the chat, or you can ask the next question and I can ask it again. let me know. Okay, then I will move on to the next question. Can you repeat the second question? Okay, Jaime wants me to repeat the second question.
Okay.
Sorry. Are the neural oscillations in the theta frequencies acting as a clocking mechanism that binds multiple circuits? I hope I'm reading the right.
I thought that I said that. It binds the oculomotor and the sensory processing circuits, right? In some way, it clocks them. Yeah, it coordinates them, because you have to suppress one when you want to be good at sensory processing. You have to suppress that oculomotor system, and if you want to shift attention to a new location, you have to ramp the other one down and release from that suppression. So I thought that was my answer to that part of your question.
There's a follow-up question to this. Aline asks, are there comparisons to blind patients?
Again, this has nothing to do with blindness, because these behavioral oscillations don't render us blind. They make us a little bit better and a little bit worse, and it's something that we do not perceive, right? So I think this is really, really an important thing, because in a sense, we live in this illusion that the sampling that we do from the environment is continuous when it is not. But that is just something that we do not perceive. So I don't think there's any specific relationship to blindness here. Whether in blind people, their sensory processing needs to be optimized in a way like this is an open question. I could totally see that. There's evidence that the auditory system, for instance, sets up these kinds of oscillations as well. And in blind people, you have this really, really enhanced auditory processing. So it's totally possible that they would have that in a different sensory domain.
There's a next question from Paloma. She asks, does the preferential sensory processing in theta frequency and the eye motor activity, saccades, share the same neural basis?
So this is a question about the neural basis of, or where the theta oscillation is coming from. Is that what that question is?
The question, I think, is more whether saccadic movement and sensory processing have the same neural basis.
No, they do not. So sensory processing, visual processing is really tied to the visual system, to posterior cortex, whereas the oculomotor system, so they influence each other. The oculomotor system is, the colliculars, the superior colliculars, and other motor structures. And then the frontal eye field has a lot of oculomotor neurons that get input from the superior colliculars, the lateral interparietal area as well. So basically, these systems influence each other. So the visual system obviously feeds into these oculomotor structures, and the oculomotor structures are feeding. They have many, many projections to the visual system, but they are, they are not coupled per se.
Thank you very much. Next question is also by Alina. And today morning we had a talk which was talking about breathing. So she asks, is there a correlation to breathing? In one of the talks today, before, we heard that neurons in primary visual cortex, or I don't know what she means, are also have oscillations at 4 Hertz.
So I think this is a really, really interesting question, and it is a question that is unresolved. So there's some evidence actually in the literature that in the medial temporal lobes, in the hippocampus, physiological signals like breathing can basically induce a theta rhythm. Whether that is something that goes across the entire brain, we don't know. I don't think that this is a rhythm that is strongly related to physiological parameters. In my thinking, this rhythm is completely dominated by the motor system. So this is an oculomotor rhythm. It is the saccadic rhythm. The 4 Hertz rhythm is in the first place, a saccadic motor rhythm. And I think that actually the motor system is controlling the entire attention network. It's not the way we like to think about attention, but I think that it's under complete motor control. And we are looking here actually at an oculomotor theta rhythm that is controlling the rest of the attention system. But again, that is something that needs to be probed. This is just a speculation, so don't take my word for it. But I don't think it's related to to breathing or other physiological parameters, even though they can induce theta rhythms in parts of the brain. That has been shown.
I believe we're a bit over time now. I haven't managed to keep track of time. So I think we have a few more questions and maybe people can write to you for it. So
sure thing.
With this, thank you very much for the great talk and dealing with all of these technical issues. And thank you for the audience. Thank you very much for being very patient. All right. Bye.
Thank you. I hope one day I can see you all in person again.
Yes, I hope so too. Bye.
Bye. Thanks for having me.